So welcome back. Now the problem I'm going to do, I'm calling Comet Approaching the Sun. So we're going to say there's a comet here with a certain mass, with a certain initial velocity. It's approaching the Sun. So imagine its distance, its perpendicular distance from the Sun is equal to, let's say, d, right? So then what I want to do is calculate as the comet is coming with a certain initial velocity, as the comet is coming, the Sun's gravity is going to start attracting the comet, right? It's going to start coming, and then velocity is going to be increasing as it's coming, right? Because the Sun is pulling it. So then it's going to come around right here. It's going to have a final velocity, very, very fast, right? And then it's going to go like this, and then start slowing down, right? And then at the end, when it comes back, right, it's going to have the same distance that it began, d initial, and it's going to have the same velocity, v initial, that it had initially, right? Energy is conserved. So what I want to calculate is the distance of the closest approach from the Sun, d final. Depending on what the initial distance is, d initial, and depending on what the initial velocity is, we can calculate what the equation for the final distance is, right? What is the principle behind this? It's two things: conservation of angular momentum and conservation of potential and kinetic energy, right? So then we have here the angular momentum initial of the comet must equal to the final angular momentum of the comet, right? And angular momentum is given by mass times the initial velocity times the initial perpendicular distance from the Sun of the comet, right? D initial. That's going to equal to the final angular momentum of the comet, right? Which is going to equal mv final and then the d final, right? So the angular momentum must be conserved. So what is this saying? As the comet is approaching the Sun, the d final is smaller than the d initial. That means v final is a lot bigger, right? So as it approaches the Sun, the comet speeds up a lot of big time, right? So then its velocity gets higher, and its temperature gets higher, and then it starts developing a tail, right? So then we're gonna cancel the m, right? Now we're gonna impose energy conservation on the comet. The initial potential energy of the comet plus the initial kinetic energy must equal to the final potential energy plus the final kinetic energy, right? What is the initial potential energy of the comet? We're assuming the comet is beginning from quite a far distance away. So its gravitational potential energy is almost zero. It's not bound to the Sun by a very strong force, right? So its initial potential energy is zero. It primarily has kinetic energy, right? So this is going to be 0, 1/2 mv initial squared, right? What's the final potential energy? Well, when it's close to the Sun, it has a potential energy. It's equal to negative gm, negative g, mass of the Sun, right? Mass of the little planet, mass of the comet, right? M divided by the final distance df, right? Plus the kinetic energy, 1/2 mv final squared, right? So the initial kinetic energy must equal to the final potential energy plus the final kinetic energy. So notice, since this is bigger, the v final is bigger than the initial v, right? This number is bigger. This number has to be negative. The potential energy has to be negative, so that this plus this must equal this. So it does make sense, right? So then we can put both of these together. The little m's can cancel. I can multiply everything by 2, and I have here v initial squared is equal to negative 2g mass of Sun over d final plus v final squared. Okay? So then what else do I know here? Well, I know v final is equal to v initial d initial over d final, right? I'm more interested in getting an equation for d final in terms of v initial and d initial. So what I want to do is I want to get rid of v final from my equations, right? So then I take that v final and I put it into here, right? And then I get what here? V initial squared equals negative 2g mass of the sun. So I'm just going to write the mass of the sun as capital M over d final plus v final squared. So I'm going to do v initial squared, d initial squared over d final squared. Okay? So then I'm going to take this here, multiply everything by df squared. I'm going to get here df squared, v initial squared, equals negative 2gm df plus v initial squared, d initial squared. Okay? So what am I solving for? I'm solving for df, right? Well, this actually becomes a quadratic equation in terms of df. Bring everything over to the left side. We have v initial squared df squared plus 2gm, okay, 2gm df minus v initial squared d initial squared equals 0. So this is almost like the equation ax squared plus bx plus c is equal to 0. And then the solution for x is going to be negative b plus or minus square root of b squared minus 4ac over 2a, right? So then I can just solve it that way like a quadratic equation. Okay? So then I'm going to say df is my x, right? So df is going to be equal to negative b. So this is my b, right? This part is my b. So negative 2gm plus or minus square root of, then I'm going to square the b, 4g squared m squared minus 4 times a, and my a is the v initial squared, right, times c, and then my c is negative v initial squared, negative v initial squared, d initial squared. Okay? Over, divide that by what? 2a, which is going to be 2v initial squared. 2v initial squared. So df is going to be what? Well, this one is going to be positive, right? The 4 is going to come out from the radical. It's going to turn into a 2. And then that 2 will cancel that 2. So you have here that 2, and this 2 cancel, right? So the 4 is gone. So then I have here negative gm. I want to simplify this a little bit. I could just say, take this and divide it into both of this, and then bring it in the radical. And then I'll write the positive first, so it'll be something like this. When it goes into radical, it becomes v initial to the power of 4, right? So it becomes g squared m squared divided by v initial to the 4th plus, when it divides into this one, it's going to be canceling the v initial to the 4th. So it's just going to be d initial squared minus, and then divide it into here, right, gm over v initial squared. Okay? So this comes out to be the general equation for the final distance of the comet, depending on the mass of the sun, right, and the initial velocity of the comet, and the initial distance of the comet, right, the initial perpendicular distance of the comet, right. So let's assume that the v initial of the comet is 1 kilometer per second. That's a realistic speed. So it's coming in from very far away from the sun, 1 kilometer per second. And this is the sun right here. And let's say the distance of the comet, the perpendicular distance, is 1 AU. Right? So this is the Earth here, like this. The Earth is, average distance is 1 AU from the sun, right? So the comet is going to come, cross Earth's orbit, and then get closer to the sun, and then get farther away, right? So if this perpendicular distance is 1 AU, that means its distance is going to be similar to the orbit of the Earth, like this. So if the comet was not attracted to the sun, it would simply go like this, right? And it would kind of cross the barely graze the Earth's orbit, right? So then let's see what's going to happen. The initial velocity 1 kilometer per second is kind of realistic. You can say the Earth's orbital speed is 25 kilometers per second. That's how fast the Earth is going around the sun. So this would be 1/25 of that speed, so which is kind of a realistic speed, right? So what would the final distance of that comet be from the sun? Okay. So then let's put all of these numbers in. the initial distance of the comet, 1 AU. So 1 AU is 1.5 times 10 to the 11th meters. So then I'm going to have to square that distance, right? 1.5 times 10 to the 11th squared. Then subtract from that gm over v initial squared. So then I'm going to do just the g times m, the mass of the sun, over the v initial, which was 10 to the third, and then if you square 10 to the third, you're going to get 10 to the sixth. Okay, so let's calculate this one by one. It's actually a pretty small number. It comes very close to the sun. 8.43, that's 84,000 kilometers, right? Okay, so that thing is going to really approach very, very close to the sun. It's going to approach very close to the sun and then come out. It's such a small portion of an AU. That comet might actually be burned up, right, by the heat of the sun. So as it goes around the sun, it gets so close, it burns up and then never comes back around, right? Now, so what's going to happen as the velocity gets bigger and bigger, right? As this gets 5 kilometers per second. What if it gets 50 kilometers per second? What if it gets 500 kilometers per second? Let's say it was coming in really, really fast. What does our equation predict? Well, the limit of this equation as v initial goes to infinity is what? Right? As v initial gets so big, this number, because this number, the v initial is on the bottom, it gets to be negligible compared to this, right? So d initial squared dominates over that. So this thing disappears, and d final equals what? Square root of d initial squared is just d initial. This number also goes to 0 as v initial gets bigger. So d final is just equal to d initial, right? As this thing gets very, very fast, it basically comes like this, curves around, and then it's going to come back out like that. So the maximum distance that this can be is equal to 1 AU, right? 1 AU, which means what? If this distance is the same as this distance, then what's going to happen? This velocity is going to be whatever initial velocity that it had, right? So that means kind of like the gravity of the sun is not affecting it. All it's doing is just making it turn. So it's just going to come 1 AU, and then it's going to end up as 1 AU, then it's going to curve around, and come back, right? So, of course, that would only happen if the v initial is very, very large compared to the initial distance, right? If it was coming at a very initial, very, very fast speed. So you can see here how to calculate now the final distance of the comet, right? How to use conservation of angular momentum, conservation of energy, and then get an actual answer, and then see if that answer makes sense, and then compare and see what would happen as the v initial gets larger and larger and larger, okay? Thank you very much.